Student, today let me start a differential equation, unit 3. A differential equation which is an independent variable, that means dy by dx, d square y upon dx square, dqy upon dx cube, is called a differential equation in which involves the derivatives. For examples, dy by dx plus y equal to e to the power x, d square y upon dx square plus x dy by dx plus y equal to 0, dy by dx का whole square plus x sin x plus 1 equal to 0. These are the more examples of differential equations. Now, in which to define a order of a differential equations, the highest derivative is known as the order of the differential equations. Degree, the power of the highest derivative is known as the degree of the differential equations. Linearity, a differential equation whose degree is 1 is called a linear differential equation. For example, in above, from a table, here we see that a differential equations dy by dx plus y equal to e to the power x. So that order is 1 and degree is 1, so that equation is a linear differential equation, in which dy by dx का whole square plus x plus sin x plus 1 equal to 0. The order of this differential equation is 1 and degree is 2, so that is a non-linear differential equation. That is the more examples of a differential equations. Now here we to find the solution of a differential equation by the following methods: first order and first degree. First method is variable separable method. Second is a linear differential equation. Third one is reducible linear differential equation. And fourth one is exact differential equation. So first we variable separation method. Let us define as a differential equation which is a form of dy by dx equal to f1x upon f2y, that means, or f2y upon f1x. So y eliminate by simplifying, here we find the f1x f1y dy equal to dx into fx. On integrating, so we get f1x dy plus f1x dy dx equal to f1x dx plus c. On integrating, so we get the required solution. For examples, now here we solve dy by dx equal to 1 plus y square upon 1 plus x. So dy by dx equal to, we can write this 1 upon 1 plus y square into dy equal to 1 upon 1 plus x square into dx. Now on integrating, the integration of 1 plus y square, that is tan inverse y, integration of 1 minus tan 1 upon 1 plus x square tan inverse x plus c. So after simplification, tan inverse x equal to tan inverse y minus tan inverse x. So c equal to, that is tan inverse y minus tan inverse x, applying the formula tan inverse a minus tan inverse b, so that we can write this tan inverse y minus x upon 1 plus xy. On comparing, here we get c equal to y minus x upon 1 plus xy. Also we can write this y equal to x plus c into 1 plus xy. So that is the required solution of a differential equation. Another example is sec square x into tan y dx plus sec square y tan x dy equal to 0. So on simplification, we can write this sec square x upon tan x into dx equal to minus sec square y upon tan y into dy. Now here we put tan x equal to u, so du upon dx equal to sec square x, tan y equal to v, so dv upon dx equal to sec square y. Now after putting these values in above integrations, so that is 1 upon u du equal to minus 1 upon v dv plus c. So integration of 1 upon u, that is log u, 1 upon v, that is minus log v, and plus c. Also we can write this c equal to log, put the value of u and v, so log 10x plus log 10y. Log a plus log b, log a into v, so applying the formula, log c equal to log 10x into 10y. On comparing, we get the c equal to 10x into 10y. So that is a required solution of a differential equation by variable separation method. Another example is dy by dx equal to 1 plus x plus y plus xy. On simplification, we can write this dy by dx equal to 1 plus x into 1 plus y. Also, we can write this 1 upon 1 plus y into 1 plus x into dx. Now on integrating, that is a log 1 plus y equal to e to the power of x plus x square by 2 plus e to the power c. So y equal to, that is e to the power x plus x square by 2 plus e to the power c minus 1. That is a required solution. Another example is x square plus y x square dy plus y square plus xy square into dx. On simplification and integration, we can write this 1 minus y upon y square dy equal to minus 1 plus x upon x square dx. Separate all each term, so we get minus 1 upon y minus log y, that is integration, plus 1 upon x minus log x plus c. On simplification, we get log 1 upon yx minus x plus y upon xy equal to c. We can write this y equal to x bracket e to the power x plus y upon x into y plus e to the power c. That is a required solution. Another example is dy by dx equal to e to the power x minus y plus x square e to the power minus y. So dy by dx equal to e to the power minus y common, so we can write this e to the power x plus x square. On simplification, that is e to the power y dy equal to e to the power x plus x square into dx. On integrating, we get e to the power y equal to e to the power x plus x cube upon 3 plus c. Taking anti-log on both sides, so we get the y equal to log e to the power x plus x cube upon 3 plus c. That is the required solution. So that is the more examples of variable separable methods. Now another method is linear differential equation or a Leibniz differential equation. A differential equation which is a form of dy by dx plus py equal to q, where p and q are a function of x or a constant. So first we find the value of p and q on comparing the given equations. Then we find the integrating factor e to the power p dx. So integrating factor, that is y equal to, so then complete solution y into if equal to q into if plus c. So that is the working process to find the solution of a Leibniz theorem or Leibniz differential equations. Now for examples here we given that dy by dx equal to e to the power x plus y. For examples, dy by dx plus 2x upon 1 plus x square into y equal to 1 upon x square plus 1 ka whole square, given that y equal to 0 where x equal to 1. So first we can write this dy by dx plus 2x upon 1 plus x square into y equal to 1 upon 1 plus x square whole square. Now here first you find the integrating factor e to the power p dx. Here p equal to 2x upon 1 plus x square dx. So that is e to the power log 1 plus x square. So there we get a 1 plus x square, that is integrating factor. Complete solution, that is y into if, that means 1 plus x square equal to integral 1 upon 1 plus x square ka whole square into if. If, that means 1 plus x square dx plus c. After cancellation or On integrating, we get a 1 plus x square into y equal to tan inverse x plus. Now put the value of y equal to 0 when x equal to 1. So c equal to minus pi by 4. So that is the required solutions. Y equal to 1 upon 1 plus x square into bracket tan inverse x minus pi by 4. Another example is dy by dx plus y tan x equal to sin x. So you can write this dy by dx plus y tan x equal to sin x. And so integrating factor e की power p dx, that means tan x into dx e की power log cos x. After simplifications, that is if equal to cos x. Y into cos x complete solutions equal to integral cot x into sin 2x dx plus c. Cos x cot x into 2 sin x cos x, we can write this cos square x sin x dx plus c. On substitutions, we put cos x equal to t, so minus sin x dx equal to dt upon dx. Putting these values in these integrals, so we get minus 2 integral t square dt plus c. After integration, minus 2t square t cube upon 3. Now put the value of t equal to cos x, so we get a y equal to 2 upon 3 cos qx plus c upon cos x. That is a required solution. Another example, 1 plus y square dx equal to tan inverse y minus x dy. So we can write this dx upon dy minus tan inverse y upon 1 plus y square equal to x upon 1 plus y square. So now first we find the integrating factor e की power p dx. So integration of 1 upon p dy, that is a e की power 1 upon 1 plus y square dy e की power minus tan inverse y. Complete solution, that is a x into if. X into if, that is e की power tan inverse y equal to tan inverse y upon 1 plus y square into e की power tan inverse y dy plus c. Now if we put tan inverse y equal to t, so we can write this 1 upon 1 plus y square equal to dt upon dx. Putting these values in above integrations, so we have x e की power tan inverse y equal to integral t e की power t dt plus c. Now applying the product rule formula, so that becomes x e की power tan inverse y equal to t e की power t minus e की power t plus c. Putting the value of t, so we get the required solution x equal to tan inverse y plus c e की power tan inverse y. So that is a more examples for a Bernoulli's differential equations. Reducible linear differential equations. The equation which is a form of dy by dx plus py equal to q into y की power n, where p and q are a function of x. So first we divided y की power n on both sides. So we can write this y की power minus n dy by dx plus py की power 1 minus n equal to q. Now put y की power 1 minus n equal to t. On after differentiation, it becomes y की power minus n into 1 minus n minus 1 dy by dx equal to dt upon dx. Putting these values in above integrations, here we get dt upon dx plus pt 1 minus x equal to q into 1 minus x. So integrating factor, that is a p dx. Another example, dy by dx plus x sin 2y equal to x cube cos square y. So first we divided by cos square y on both sides, so we can write this cos square y dy by dx plus 2x tan y equal to x. Now here we dt upon dx plus 2xt equal to x. Integrating factor e की power 2x dx e की power x square. So that is in t into e की power x square equal to x square e की power x square dx plus. So log y e की power x square, here we put x square equal to t. So 2x dx equal to dt upon dx. Putting all these values and after integration, it becomes a complete solution. Tan y equal to 1 by 2 x square minus 1 into e की power minus x square into c. That is a required solution. Another example, that is a more example of Bernoulli's differential equations.